Hello, solids. Let's talk about solids. Okay, yes, you're saying, yay, I love solids. I want to talk about solids. Okay, particles and solids are in constant motion, but they're nearly touching each other. So gases are everywhere. They're in constant motion and they're like whacking into each other's liquids a little bit closer. Remember, they're coming out of my cup. Solids, glass, paper, weight. Not so much moving. The glass is not flying off. This glass is not going to evaporate when I come back, right? It's a solid. However, the molecules are in constant motion. How do we know this? Because if I made this paperweight. I'm not kidding. I have pictures. I made this. And what did I do? I melted glass. I took glass and I melted it and I reformed it into something else. Because what did I do? I heated up the particles and they started moving around. They started jiggling and wiggling, and they only move a small amount, but making diffusion is much slower in solids than in liquids. Particles in crystalline solids have a ordered arrangement. Particles in amorphous solids are arranged in random fashion. So, crystalline and amorphous solids. So, crystalline solid, rings, metals, like iron, silver especially. And you whack on those, you whack on it with a hammer, it doesn't do anything, right? That's what's great about it, because I don't hit myself with a hammer all the time, but I do fall, I hit myself, and that's the good news about my ring, it doesn't shatter. So, metals, crystalline structure. You can whack it with a hammer. Good. It will melt, right? That's how it got forged into this ring. But it has a very distinct melting point. And you can forge it into this ring, and it's not like when it gets hot, because it's ready and it gets hot. My ring doesn't melt off my finger. It's a solid. You can heat up the molecules and move them around, but it's very high temperatures. Hence, that's why we are the Mr. Roy. Now, amorphous solids, my awesome paperweight that I made, it's random. These particles are more random because if I hit it with a hammer, don't hit my beautiful paperweight with a hammer. If you did, it would shatter in a bunch of pieces. If I dropped it, it would shatter. This is an amorphous solid. So there's two different kinds of solids. There's actually a bunch of other stuff about solids that we are not going to talk about because that's all I really care about in terms of solids. Okay, let's talk about change of state real quick. Change of state. When a solid is heated, boom, or my cup of water, when I heat these things, the molecules begin to what? They kind of begin to go crazy. When I have to heat this hot. If you've ever blown glass, you know it has to be really, really hot. When the solid is heated, the molecules begin to do all kinds of great stuff. They stretch to try and stop you from messing with them. Stretch. They bend, and they vibrate. They do all the stuff. They're just like going crazy. They're wiggling, they're jiggling, they're moving vigorously. They have a bunch of energy, and then all of a sudden they change state. They melt, or they become gas, or they do something else. If enough energy is added and the motion becomes vigorous enough, particles start to break free from one another, and the substance starts to melt. So, if I was going to try and melt this glass, it has to be really hot. You're going to start seeing, if you've ever seen like a pot boil or something, the energy, it's moving, right? The whistle blows on the kettle. Things are moving. Things are actually moving around it. You don't think of it as that way, but that's what's happening. The molecules are moving. It's causing motion. It's causing melting. What is the heat of fusion? Heat of fusion is, let me put it in red so you know I'm serious. The quantity of heat required to completely melt 1 gram of substance once it has reached its boiling point. The quantity of heat required to completely melt 1 gram of substance once it has reached its boiling point. So that is the heat of fusion. There is a super handy chart all about heat of fusion in your book. You should look it up. Okay. It tells you the different heats of fusion, and it'll tell you how hot things need to be. Okay. When a liquid is heated, all the added heat goes into raising the temperature. That's what happens first. You're raising the temperature. So you're waiting for it to boil, waiting, and what's it doing? It's getting hotter, right? You shouldn't touch it, but it's not boiling yet. You're waiting, or the liquid is heated, all the heat goes into raising the temperature of the water. Because that's what you're doing. You're raising the temperature, Once the boiling point is reached, though, it goes into, this just sounds like you're doing something awesome, freeing molecules from their neighbors as they escape into the gas state. Doesn't that seem like it should be a movie? It's like a hero movie. I just released all the molecules from their evil neighbors, and now they're in the gas state. Like, my poor water. I'm going to boil it, and then I'm going to release it. I'm going to release all those hydrogen bonds. I'm going to release it. Go! Be free, hydrogen and oxygen molecules. Go forth. If I boiled my water, that's what I would be doing. I would be freeing them. Oh, go free. That's what happens. Actually, what am I doing at first? At first, I'm just boiling the water. I'm making it hot, right? Because I probably want some tea. And I'm just making it hot. And it's doing nothing. I mean, some is evaporating off a little more, but basically, it's just getting hot. It's not doing anything. It's just sitting here getting hot. Yeah, certainly things are bouncing, but not necessarily more than they were. They're just there. It's just getting hot. And then all of a sudden, the boiling starts, right? All of a sudden, it's like, be free, be free. And the steam is coming, and all kinds of good things are happening. It's a change of state. Heat of vaporization. Let's talk about that. Heat of vaporization. Quantity of heat needed to completely vaporize. To completely vaporize a liquid at its boiling point. So if you want to completely vaporize a liquid, you have to take into account, if I have a huge vat of water and for some reason I want to just evaporate all of that heat out, I have to calculate how much am I going to need? How much actual energy? Heat. The word here should be heat. How much heat am I going to need to completely get rid of? How much heat am I going to need to get rid of all of my wonderful water in my beaker cup? Okay, a volatile compound. What is a volatile compound? A liquid with a low heat of vaporization. And we talked about some of these. A volatile compound is something with a very low heat of vaporization. So it doesn't take much to just, it's gone. Poof, gone. We have some of these chemicals, we have to keep them, you have to keep the lid on. You can't just leave the lid off or it's a volatile compound. It has a low heat of vaporization. So if it gets just a little bit hot, it goes into a vapor. So here's a super fun graph of awesomeness. So we're in a solid state. We're ice. Just go with me because we know all about ice. So at some point, you're solid. So you start out at -80 degrees because your freezer is really cold. And at this point, you're adding heat. Nothing's happening. Absolutely, there's nothing happening. And then all of a sudden, melting point. Awesome. Now you're melted. Now you're what? All of a sudden, you're a liquid. Now, again, I'm trying to boil this. So you're still a liquid, All that energy is just going to raising the temperature, and then boom, you are a gas. You've been free, and you're a vapor. You have been vaporized. You are vapor. Okay, this is all related to our friends' intermolecular forces. Intermolecular forces. Yep. Intermolecular forces. Not as cool as the force, but nonetheless forces. Remember there was 3: dipole, London dispersion, and hydrogen bonds. These are intermolecular forces. They are strong. Then large amounts of heat must be added to overcome them. So if you want to overcome the forces, you have to overcome them. You need heat. You need heat to overcome the forces. the heat of fusion and vaporization will be large if you want to overcome them. If you want to overcome all the molecular forces with different types of, you can look on the chart and it'll show you the heat of fusion and the heat of vaporization and the vaporization for each element on that chart. And you'll know how much energy you need to add to overcome the intermolecular forces. So that is all of chapter 8. Just one more time, because it's fun.